not with some galvanometer. This is galvanometer. Now this is the magnet we have. This is the magnet, and magnet will produce the magnetic field. Magnet will produce the magnetic field, and the effect or the strength of the magnetic field produced by the magnet will be here also in the region of coil also. Matthew, will it be or not? The magnetic field produced by this magnet will be here also, na?
Yeah, sir. Yeah.
Like this. If you will draw the magnetic field line, so these magnetic field line will be like this.
It pass through the coil. Yeah.
Yeah. So what will happen now? What will happen? It means first point to remember. First point. Otherwise, you will get confused. Due to this magnet, there will be some magnetic field in the coil region. There will be some magnetic field in the coil region. And now, suppose this magnet starts moving towards the coil. So what will happen? Suppose initially this magnet is here. Now finally this magnet is here. So what will happen? Magnetic field in this region will increase or decrease? Matthew, when the magnet will be close to the coil?
It will increase.
Increase. Very good. Increase. Okay. Why increase? Because suppose this is some wire, this is the magnet. Now due to this magnet, there will be some magnetic field here on the wire. And when the magnet will move closer to this wire, so magnetic field strength due to the magnet at wire will increase. Or you can say, if this wire is moving towards the magnet, then also magnetic field on this wire will increase. This is not the wire, this is a pen. Just imagine this is a wire. Okay, this thing is clear now. And what is magnetic flux? Magnetic flux is VA cos theta. So here area is not changing, theta is not changing. Now you can say this magnetic flux is directly proportional to the magnetic field. Magnetic flux is directly proportional to the magnetic field means when this magnetic field will increase, here the magnetic flux will increase. So what is the physical meaning of magnetic flux? What is the physical meaning? Hello Nawal. So I am discussing just basic thing. Okay, this is the magnet, this is the coil. These are the magnetic field lines due to the magnet. So due to this magnet, there will be the magnetic field. When this magnet will move away from the coil, so at coil the magnetic field will decrease. When this magnet will move towards the coil, then the magnetic field will increase. And what is magnetic flux? VA cos theta. Area constant, theta constant. So this term will remain constant. So your magnetic flux on the coil, or you can say magnetic flux linked with the coil, is depending upon the magnetic field. So when the magnet will move from this position to this position, magnetic field will increase, and due to increase in the magnetic field, magnetic flux at coil, or you can say linked with the coil, will increase. What is the meaning of the magnetic flux? Number of magnetic field line. Actually, magnetic field lines are not real lines. These are the imaginary lines. We draw the magnetic field and electric field line because for understanding, for the feeling, okay, for the feeling of the magnetic field, for the feeling of the electric field. Suppose this is a magnet. So there will be no magnetic field line. Magnetic field line are just imaginary lines, but there is a magnetic field. So to show that magnetic field, we draw the magnetic field line. So here, this is the magnet, and due to this magnet, I have drawn the magnetic field line. So what will happen when the magnet will move towards the coil? Magnetic field will increase, or you can say magnetic field line density will increase, or you can say the magnetic flux will increase. Okay. Suppose this magnet is moving away from the coil. This is the coil. So what will happen at coil? The magnetic field will decrease. So if this magnetic field will decrease, this magnetic flux on the coil or linked with the coil will decrease. Magnetic flux on the coil or linked with the coil will decrease. Now I think this thing is clear. This concept is used by the Faraday. Now Faraday law is nothing for you. The main point is to understand how the flux is changing with respect to coil. So write down the heading, Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Write down the heading, and this is the statement. This is the statement. So whenever magnetic flux linked with the coil change means change can be increase or change can be, if something is changing means it can be increase or it can be decrease. Okay, if something is changing, suppose the velocity is changing. Initially, the velocity is 2 meter per second. Finally, the velocity is 4 meter per second. Velocity here is increasing. Increasing means changing. Suppose the velocity is decreasing 2 to 1 meter per second. This decreasing is also a change. Change means either increasing or decreasing. So you can say whenever the magnetic flux linked with the coil change here meaning increasing or decreasing, an EMF is induced in the coil, and this induced EMF is proportional to the rate of change of magnetic flux linked with the coil. Okay, so whenever the suppose here is a magnet. Again, I am taking one magnet. This is the magnet, North Pole and South. Magnet have two poles, North Pole and South Pole. And now you can imagine, try to imagine this in your mind. What is happening? This magnet is doing the motion. The motion can be either away from the coil or towards the coil. So suppose this magnet is moving towards the coil. So what will happen? If the magnet is moving, the magnetic flux is changing or increasing with respect to coil or linked with the coil, then what will happen? There will be an induced EMF. There will be an induced EMF in this circuit. See, there is no wiring connection between the magnet and the coil, and here is no battery. Then also there will be some current. See the phenomena, and this phenomena changes the word. Changes the word. Phenomena of electromagnetic induction. We got the alternating current from here, and that changes the word. So due to the magnet motion, there will be some current. Okay, now Matthew, tell me why this due to the motion of the magnet, why due to the motion of the magnet there will be the current in this circuit, or there will be the EMF? Just try to think.
The because there is already an electric field happening there. When you apply magnetic field on it, and induce EMF is formed.
So in simple words, you can say when the magnet is moving towards the coil, magnetic flux is increasing, and due to increase in magnetic flux, induced EMF will be there in the coil, and due to the EMF, current can be there. So according to the Faraday law, says that I will write small e as induced EMF. Okay. So according to Faraday law, induced EMF is directly proportional to. Before that, we should know. Just a minute. We should know what is happening here. Okay, suppose initially at time t1, at Suppose any time t1, t1 you can say at 2 p.m. Okay, at 2 p.m, 2:10 p.m. At time t1 your magnet is here, your magnet is here, your magnet is here na. And if the magnet is here, so there will be the magnetic field here. Due to this magnet, there will be the magnetic field. So at that time there will be some flux or magnetic flux here. Suppose that flux is phi 1. Phi 1 is the magnetic flux when your magnet is here. So phi 1 is the magnetic flux linked with coil. This is coil, this is C1 is representing the coil 1, coil. Magnetic flux linked with coil is just a wire. Magnetic flux linked with coil 1. Now after that this magnet is moved to this position. So at some time, after some time t2, this magnet will be suppose here. We will say at time t2. Matthew, do you know Hindi?
Yeah, sir, kind of.
Nawal, do you know Hindi?
Yes, sir.
And Nafisa, I think you don't know.
No, sir, I don't know.
Okay, no problem. I'm just asking. This is phi 1, and this is, and due to when the magnet will be here, when the magnet will be here, there will be the magnetic flux. Okay, there will be the magnetic flux of due to this magnet here. Okay, so phi 2 is the magnetic flux linked with coil 1 at time t2. This is at time t1. Okay, first thing, remember this thing. Okay, so what, when the magnet is moving from this point to this point, from this position to this position, flux is changing from phi 1 to phi 2. Okay, so change in flux is represented by, suppose delta phi. This delta, what is this? This is delta. This delta is representing the change in flux. If it is written that delta v means change in velocity, if written there delta a, change in acceleration, delta v, change in magnetic field, this delta is representing the significant change. Okay, if I am writing dv, where v is the velocity, this dv is representing the infinitely small change. Okay, remember both these points. Actually this is the part of the calculus. This d, when we write dv and when we write dx, when we do the differentiation, this is the part of the calculus. And this thing came from the Newton when he was just driving the uh, law of gravitation. Then he discovered the calculus, because without the use of the calculus at that time there was only algebra, but algebra is not able to explain all the concepts properly. So he himself discovered the calculus and then explained his theory. Okay, by the way, so delta phi is the change in flux. Flux means magnetic flux. Delta t, delta t is change in time, change in. So delta phi, what you will write? Final minus initial means phi 2 minus phi 1, and delta t you will write t2 minus t1, t2 minus t1. Okay, so according to where I should write the Faraday law. Okay, so we can write na, we can. Okay, no problem, we can write here. So basically, Faraday says that EMF induced in the coil, here is the coil, EMF induced in this coil due to the change in magnetic flux is directly proportional to delta phi by delta t. Means, what is the meaning of delta phi by delta t? Change in flux with respect to change in time. Change in flux per unit time. Like change in velocity per unit time is acceleration. Change in displacement per unit time is velocity. Like change in flux per unit time is directly proportional to the EMF, or EMF is directly proportional to change in flux with time. So from this you can, when you will remove this proportionality sign, you will get k delta phi by delta t, k delta phi by delta t, and this k is equal to -1 for all system of units, for all system of units. We have SI system of units, international system of units, we have CGS, MKS, FPS. So in all system of units, this k value is -1. So when you will put this value of k -1, so finally you will get EMF is equal to minus of delta phi divided by delta t. So minus delta phi by delta t, this will be your formula you will get. So induced EMF is equal to negative of delta phi by delta. Now, like in the chapter current electricity, I have told you current is change in the charge divided by change in time, or charge divided by time. Here also we have EMF, change in flux divided by change in time. There we have discussed average current and instantaneous current. I have told you we calculate average for finite interval of time, but finite interval of time means if someone is asking what will be the EMF from 2 seconds to 3 seconds, means he or she is asking the average EMF. If someone is asking what is the EMF at t equal to 1 second, at t is equal to 1 second, mean at an instant of time, then he or she is asking the instantaneous EMF. So we will divide this in two parts. First will be average EMF, and after instantaneous. So average EMF is simply this. This is the average EMF for finite interval of time. So average EMF induced in the coil will be given by minus of delta phi divided by delta t. Okay. For the induced EMF, you will write limit delta t tending to 0 and minus of delta phi divided by delta t, and this can be written as simply minus of d phi by dt. I have told you earlier that this d phi is representing the very small change in the flux, and dt is very small change in time, d phi by dt. This is a differential form. Okay. Now if I want to calculate the current, what will be the current in this coil? Their EMF is induced now due to the change in the magnetic flux. Now for this coil, if I want to calculate the current, we know that V is equal to IR. If I want to calculate the current, so I will write V by R. What is V? V is the potential difference, or you can say voltage, or you can say EMF, and divided by the resistance. So current in the coil, current in the coil. So this is the coil now. We have this coil. See, this coil we have, I have drawn here. C1 coil, galvanometer is there, and there is a induced current also, not due to the induced EMF I have told you. And this coil is made up of wire. We know that the wire will have some resistance. So here we are saying resistance of the coil. So how we will calculate? So current in this circuit, or you can say current in the coil, is given by EMF divided by the resistance. And what is EMF? EMF is minus d phi by dt. I will use this instantaneous EMF. EMF is minus d phi by dt. So put instead of E. So this will become 1 by R minus of d phi by dt. Okay. Finally, what you will get? The current in the coil will be minus of 1 upon R d phi by dt. Okay. D phi by dt. So what is current? Current is charge per unit time, charge flowing per unit time. So now if I want to calculate the charge flowing in this coil, charge induced you will say, because current is induced, that is why you will say charge is charge induced. So for calculating that charge, we know that the current is given by dq by dt, charge divided by time, instantaneous current I am writing here, dq by dt. So charge can be written as I is the current into dt, and you know what is the value of current? Current is minus 1 by R d phi by dt, minus 1 by R d phi by dt, and here is one more dt, and this is gone with this. Okay, so here what will be the charge induced? Minus of d phi by R will be the charge induced in the coil. Okay, note down. This small e is representing the induced EMF.
Scroll down, sir.
Nawal and Fiza. Should I scroll down?
Yes, sir. Yes, sir.
Okay, fine. Matthew, you are from South India, in India,
Yes, sir. Kerala. Kerala.
Kerala. Okay. So, languages, what are the languages there? Malayalam and all that.
Only Malayalam. Only
Only
Malayalam.
Malayalam. Okay.
But I do know a bit of Hindi though, because I learned it
Yeah.
in school, so I can.
So, have you seen any movie in Malayalam?
Yeah, of course, sir. Yeah.
Very nice.
What about you, sir? Have you watched?
Actually, I didn't get the movie in Malayalam, but I used to watch the South movies. I like South movies, but I watch or I see the dubbed version in Hindi.
Ah, I see.
Yeah, I know only two languages, English and Hindi.
Ah, I
And
see. Yeah,
basically,
yeah.
hmm. Here this sign, na galvanometer sign is tilted, means this arrow is tilted like this. So this showing that there is some deflection in the galvanometer. So I told you what is the use of the galvanometer to detect the current in the circuit. So here this is just a pointer and this pointer is like this. So like this means here is some current in the circuit. Should I scroll down?
Oh, yes, sir.
Okay.
Yes, sir.
Okay. Charge induced. After this, we will solve one very easy question. Then I will take the question of thing NCRT. Should I move now?
Yes, sir. Finish.
Okay. Note down this also. You already know, I think. Means in open circuit, if the circuit is open, suppose this is the circuit, na? I have just open it like this. Just a minute. I have opened it. This is the open circuit. I have disconnected this wire. So what will happen? Current will be zero, na? Current will be zero in this circuit, but EMF will not be zero. So in open circuit, induced EMF exists, but induced current is zero. In closed circuit, both EMF and current exist. Okay, just write down this also. This is not very. Okay, so now we will solve one question, and before that question, I want to know whether you know how to differentiate the function or not. Okay, so suppose this is the function y is equal to, suppose this is the function y is equal to 3x to the power 5. So here written, this is the question, and here written differentiate y with respect to x. With respect to x. Suppose one thing more. Suppose I am saying uh, here a is equal to 10 and b is equal to 5. If I will say divide a by b, divide a by b. So I think this is easy for you and this will be difficult for you. This is algebra and this is the calculus. This is algebra. What you will do here? Simply divide a by b. A is 10, b is 5, this is 2, and this is finished. Now this differentiate y with respect to x. Here, here I have not written divide y with respect to x. You will do divide y with respect to it. But here what you will do now? Here you are applying some different thing. You are just differentiating y with respect to x. So how you will write na differentiating y with respect to x? dy by dx. This is the differentiation of y with respect to x. How you will do that? What I have told you, this is the power, and you will multiply this power here. So this will become 5 3s are 15, and this is x to the power 5. So here you will remove one power. Remove one power means here is 5, here is become 5 minus 1, 4. Suppose here written y is equal to x is written, and I am saying differentiate y with respect to x. What you will do? What you will do? Here x to the power 1, x mean x to the power 1. So what you will do? Here you will multiply. Here you will multiply. Here you can write this as this 1 into x into 1. So here you will multiply this 1 with 1. So it will become 1. And here x to the power 1. When you will minus 1 from x to the power 1, it will become x to the power 0, and anything to the power 0 is 1. So answer will be 1. Okay. So this type of differentiation we will use in the next question. Okay. So okay, so flux linked with the coil, there is some coil and flux linked with the coil phi. Phi is the flux. Okay, magnetic flux linked with the coil. Right here, magnetic flux. So magnetic flux linked with the coil is this. This is the magnetic flux. T is representing the time. T is representing the time. So they are asking induced EMF in 0 to 2 seconds. In 0 to 2 seconds, what will be the induced EMF? So means they are asking the average EMF, because here is some time interval. After that, they are asking induced EMF at t is equal to 2 seconds. At t is equal to 2 seconds means they are asking the instantaneous. Okay, they are asking the instantaneous EMF. So first we will calculate the average EMF, then we will calculate the instantaneous EMF. Okay, so phi is given. Right. Phi is given 3t square plus 2t plus 1. So first part. What is average EMF is equal to minus of delta phi by delta t. Delta phi means, what is the meaning of delta phi? Delta phi is phi 1 minus phi 2. Sorry, phi 2 minus phi 1. Delta phi is phi 2 minus phi 1. What is the meaning of delta t? T2 minus T1. First calculate delta t. What is T2? T2 is this 2 second. 2 second is will be the T2, and this is your T1. So this will become T2 minus T1, 0 minus 2 minus 0. It will be 2 seconds. Now, how you will calculate phi 2? How you will calculate phi 2? So for phi 2, you will put t is equal to 2 in this equation. So this will become 3, and instead of t you will put 2 plus 2 into 2 plus 1 minus for phi 1. What we will put here? T is equal to 0. You will t for t you will put t is equal to 0 in this equation, then you will get phi 1. So t equal to 0 means 3 into 0 square plus 2 into 0 plus 1. Okay, so this will become 17, and this will become this is 0, this is 0, this is minus 1. So this will become 8. This will become 8 Weber. Unit of phi is Weber. What is delta t is this? So now put all the values. E is equal to minus of delta phi. What is delta phi? Is minus of, this is 8 and this is 2. Oh, sorry. This will be 16, not 8. This will be 16 Weber, and this is 2. Here is 16. Here is 16. Phi 2. This will become 8 volts, because unit of EMF is volt. Second part. In the second part, they are asking the instantaneous EMF, means d phi by dt. They are asking d phi by dt means, d means very small change. And what I have written here in the, when we are solving for the differentiation, dy by dx, how to calculate dy by dx. Similarly, we will calculate d phi by dt. So here is your minus sign, and here dy dt, and here put the value of phi. 3t square plus 2t plus 1. 3t square plus 2t plus 1. So can you differentiate this 3t square? This will be multiplied here. Here is minus sign. This is the minus sign. This will become 3 to the 6. And here is t square, means here will be only t, means t to the power 1. Okay, here will be 2. Because this is t to the power 1. When you will from the power 1, when you will subtract 1, then it will become only 2, means x to the power 0, 2. So this will be your EMF, instantaneous EMF. And at what time they are asking? At t is equal to 2 seconds. At t is equal to 2 seconds. Now put the value of t here. This is minus, this is 6 into 2 plus 2. So your answer will be minus 14 volts. Minus 14 volts. Write down this question. So this is the magnetic flux linked with the coil is this phi. Write down fast.
So I can scroll down.
Okay.
Sir, can you scroll up? I didn't finish.
Fine.
Yes, sir. Yes, sir. Can you scroll down?
Yeah.
Sir, can you scroll?
Yeah.
Yes, sir, finish.
Okay. So we will discuss one more question on this topic, and this question. Note one thing here. Suppose I have written delta phi. This is delta phi. I have written this phi 2 minus phi 1. No? So I can write now delta phi means change in the flux. Change in the flux means I can also write this final flux minus initial flux. Okay, this thing you should know. So we will solve this question now. Okay. They are saying a coil of cross section area A lies in uniform magnetic field. A coil of cross section area A lies in a uniform magnetic field with its plane perpendicular to field. Okay. In this position, normal to the coil. Normal to the coil means suppose this is your coil. This is your coil, and this is the normal to the coil. The span is representing normal to the coil. So they are saying normal to the coil makes an angle 0 with the field. Okay. After that, the coil rotates at a uniform rate. At a uniform rate to complete one revolution in time t. So what is happening here na, in this question? Try to think the question practically. Suppose this is your coil na. So with this plane perpendicular to the field. Okay. So this is your coil na. This is your coil, and this is the plane of the coil. This, or you can say this. Suppose this is the plane of the coil, and magnetic field. Magnetic field is making an angle of 0 degree with the plane of the coil. Okay, magnetic field is making an angle 0 degree with the plane of the coil. So this is the plane of the coil, and this is the magnetic field. So magnetic field is making an angle of 0 degree with the plane of the coil. So what is happening now? This coil, after that, this coil is rotating. Initially, this is this part you are just watching now. You are this part, this camera part. So what is one complete rotation means? This coil is rotated like this, okay, like this, and again like this. So this is the complete rotation. So for the complete rotation, the coil have to rotate 4 times 90-degree angle, means 360. 190, another 90, another 90, and another 90. So this thing you should know. And time taken to complete one rotation is known as the time period. So in one time period, the coil will rotate. In one time period, the coil will rotate 360 degree. So okay. So initially we have a coil of cross section area A lies in the uniform magnetic field with its plane perpendicular to field, and they are saying in this position normal to the coil makes an angle of 0 degree. So suppose this is your coil initially. Okay, this is your coil, and magnetic field is like this. This is the magnetic field. This is the magnetic field. And in this case, na, this is I will draw it like this. This is the coil, so this will be the area vector. Area vector will always be perpendicular, na? Area vector will always be perpendicular to the magnetic field, and this is also the direction of magnetic field. Okay, so they are saying in this position, normal to the coil makes an angle 0 degree with the field. So see, the angle between the area vector and the magnetic field vector is 0 degree. So theta here is 0 degree in this position. Okay, this is the first position. So now after that they are saying the coil rotates at a uniform rate to complete one rotation. The coil is rotated through one rotation in time period t. They are saying find the average induced EMF, average induced EMF in the coil during the interval when the coil rotates by 0 to 90 degree. So answer first. When the coil rotates from 0 degree to 90 degree means this is the initial condition of the coil. Okay. This is the initial condition of the coil. This is the area vector here. Here is the magnetic field. For rotating 90 degree means this coil is rotated like this. For rotating 90 degrees, the coil is rotate like this. And if the coil is taking time t for the rotation of 360 degree, for the rotation of 90 degree, what will be the time taken by the coil? In 360 degree rotation, time taken by coil is capital T. This is given in the question. So in 90 degree, what will be the time? T by 4. Is it or not? See here. This is your coil, na? This is your coil. So in rotating 4 times 90 degree angle means complete rotation means this coil will rotate 1, 2, 3 and again 4. So this is one complete rotation. In doing the complete rotation or for complete rotation means this coil have to rotate 360 degree angle. While rotating the 190 degree angle, the coil have to rotate through 90 degree. The coil have to rotate 90 degree, and in 360 degree the coil is taking the time t. So in 90 degree the coil will take time t by 4. So like this you can just, this is the initial condition of the coil. So time taken t by 4 plus t by 4 plus t by 4 plus t by 4. So 4 times when you will add t by 4, it will become t. Now got it, Nawal?
Yes, sir.
Nafisa and Matthew?
Yes, answer.
Yes, sir.
Okay. So now this question is, you can do it now easily. So one more thing here, that is very obvious. Your magnetic field is in this direction. Magnetic field is along this direction. Now this is also a direction of your area vector. Now what has happened? Magnetic field, direction of the magnetic field is not changing, but this coil is moved 90 degree. So the angle between the area vector and the magnetic field will become 90 degree when the coil is rotated through 90 degree. So you can write here, when coil rotates to 90 degree, theta will become 90. What is the theta? Theta is the angle between the magnetic field and the area vector. What is here theta? Initially theta is equal to 0. Initially theta is equal to 0. This is the initial condition. So finally, where is your coil? At theta is equal to 90 degree. Initially, where is your coil? At theta is equal to 0 degree. Okay. So initially, theta is equal to 0 degree. Finally, theta is equal to 90 degree. So neither the magnetic field is changing, nor the area of the coil is changing, but only theta is changing. So initial flux will be, formula of the magnetic flux you should know, phi is equal to VA cos theta for plane area. So magnetic field is B, area is A, cos of 0 degree. So this will become cos 0 is 1, so this will become VA. Here you will write phi final, VA cos 90. Cos 90 is 0, so your final flux will be 0. Now they are asking to calculate the average EMF. What is the average EMF? Minus delta phi by delta t. I have told you that delta phi can be written as final flux minus initial flux divided by delta t means change in time. Initially the time t is equal to 0. Now the time is t by 4. In rotating the coil through 90 degrees, the time is t by 4. So you will write here delta t is t by 4 minus 0. So now put the value. Final flux is 0, initial flux is VA. Here is t by 4. What will be the answer? Minus minus plus, this plus VA and this will become 4 VA by T. 4 VA by T will be your answer. And what is the unit of the, this is volts. First part. The second part you will do by yourself. This is your homework. When the coil is rotating from, now initially your coil is like this. After that your coil is rotated through 90 degree. Now from this 90 degree to 180 degree, when the coil is rotating, you have to calculate the average EMF induced. Okay, write down the question and answer both. And this is a, I will say, a good question. After this, we will discuss the Lenz law.
Yes, sir. Finish.
Okay. Matthew, completed. Nawal, completed.
Yes, sir.
Okay. Just a minute.
Yes, sir. Yes, sir.
Okay.
Yes, sir. Finish.
Okay. Okay. So Matthew, done.
Yes.
Done. Okay. So Lenz law. Lenz law is very important topic like Faraday law. So Lenz law is basically based on the energy conservation. So Lenz law says that earlier we have discussed that there will be the induced current. There will be the induced current due to the change in the magnetic flux. But Lenz law will tell you the direction of the induced current. So according to the Lenz law, direction of induced current is direction of induced current is such that it opposes its cause, that is change in flux. Means in the coil the current will induced in such a way that it always opposes change in flux with respect to coil. Okay, first thing you should know for the Lenz law, you should know these things. We have discussed this in the last chapter. In last chapter I have discussed this. A current carrying coil behaves as magnet. Okay, so if the current is in clockwise direction, then this phase will behave as south pole, and if the current is in anti-clockwise direction, then this phase will behave as a north pole. Means a current carrying coil will behave as a magnet. Here is south pole, here is north pole. Okay. So Lenz law can be explained with the help of the questions. So there are one first type of question you will have. Suppose this is the you, this is you, this is you. You are observing. You are observing. This is some coil. In this coil, initially there is no current, and here is some magnet. Here is some magnet. So now see. Suppose this magnet is moving towards the coil. This magnet is moving towards the coil, and I have told you earlier. When there is a motion of the magnet, there will be the current in the coil. The coil can be in circular shape, the coil can be in square shape, the coil can be in rectangular shape. Okay, so why there will be the magnetic flux? Because why there will be the induced current? Because when the magnet will move towards it or away from it, the magnetic flux linked with this coil will change, and due to that there will be EMF, and due to that EMF there will be induced current also. So the direction of the induced current will oppose the change in flux according to the Lenz law. So the current induced in this coil in such direction that that current will oppose the change in the flux. And what is the cause of the change in flux? The motion of the magnet. So basically the current will induce in coil in such a way that it will oppose the motion of the magnet. So you can see here this north pole is approaching this coil. So the magnet, not the magnet, the induced current will generate here the north pole. North pole means this type of current you will have. Means the current will be like this. Current will be anti-clockwise. Okay, so in this coil the current will be anti-clockwise. Okay, let's see this. Suppose this is the coil and this is the magnet, and this magnet is moving away from the coil. So here what is happening? If this magnet is moving away from this coil, so magnetic flux linked with this coil is decreasing because the magnet is moving away. Decreasing means the magnetic flux linked with this coil is changing. So what is the cause of change in the flux with respect to this coil? The motion of the magnet. So this in here there will be the induced current, and that induced current will oppose the motion of the current by producing either north or south pole depending upon. So here north pole is produced because why? Because north pole and north pole repel, and the motion of the magnet will be stopped. And here this north pole is going away from the coil, but due to the induced current, the motion of the magnet should be reduced. So here which pole should be there? South pole, na? South pole should be there. South pole. South pole means the current will be like this. Clockwise current. Current will be clockwise. So in this way you can get the direction. Okay, this already discussed. Okay, so there is one more question I will take. Please focus. This is one coil and sorry. This is one coil and this is another coil. This is one coil, this is another coil, and this is your magnet. This is north pole and this is south pole. And this magnet is moving in this direction. This magnet is moving in this direction. So if this magnet is moving in this direction, so what is the direction of current in this coil and in this coil? So start from this coil number first. So as the magnet is going away from the coil, so this magnet is moving, this magnet is moving away from this coil. So what there will be some induced current here, and that induced current will try to stop the motion. So here south pole will be there. South pole will be there, means the direction of the current will be clockwise. Direction of the induced current I will be clockwise. And now here for this coil, this magnet is going towards the coil, means this magnet is increasing the magnetic flux with respect to this coil, but the induced current will try to decrease that flux. And what is the cause of increasing flux? The motion of the magnet. So the motion of the magnet can be stopped by producing here a south pole, because south and south will repel. So there will be a current here clockwise. Basically, the motion of the magnet should be stopped. So now we will discuss how we will calculate the direction of the induced current. So direction of the induced current is simply given by the right hand rule. Suppose this is your magnetic field, induced magnetic field. This is your induced magnetic field, and this is the inward magnetic field. So what you will do? First, you will place your thumb in the direction of the magnetic field, okay, and curl your fingers, and the sense of curling of your finger will give you the direction of the current. So see, this is the inward magnetic field now. So do your thumb inward. Inward means something away from you, inward, and now curl. This curling is in the anti-clockwise direction, so you can get the direction of the induced current. Suppose your magnetic field is outward, so what you will do? Your thumb should be outward like this, and you will curl your finger, so you will get the anti-clockwise direction of the current. Okay, anti-clockwise direction of the current you will get. Place your thumb in the direction of the magnetic field. Curvature of your finger will give you the direction of induced current. So here your magnetic field is inward, so you will do your thumb inward. Inward means away from you, and you will curl your finger. So anti-clockwise direction will be the induced current direction. Here the magnetic field is outwards. Magnetic field is outward, so you will place your thumb outward and curl your fingers. You cannot curl your finger like this. Only you can curl your finger like this. Okay. We cannot curl. If someone is thinking that thumb is towards me and curling your finger like this, this is not the. You will curl your finger normally. Okay, like this. So here you will get the anti-clockwise direction. So according to the direction of the magnetic field, induced magnetic field, you will get the direction of the current, induced current. Or this can be the other magnetic field also, not induced. If there is a magnetic field inward, then current will be clockwise, and outward, then the magnetic field is outward, then the current will be anti-clockwise. Okay, now write down this Lenz law. I have told you in the magnetic movement, a current carrying coil behaves as magnet. So if current is in clockwise direction, then that phase will behave as south pole. If current is in anti-clockwise direction, that face of the coil will behave as north pole, and in the opposite side there will be some south pole. Write down first heading Lenz law and then write the statement. Scroll down.
Yes, sir.
Matthew?
Yeah.
Okay. So I think now you can solve these types of questions. Basically, you should focus on to stop the motion of the magnet, because the motion of the magnet is responsible for change in flux with respect to this coil. So accordingly, you will decide which pole or which is what is the direction of the current here in the coil. This as I have written intentionally like this, okay? Because this is while you will write as in this form, na, so you can get the direction of the current, this arrow from this arrow, and n also.
So if we were to introduce the south pole into the loop, also it will become a south pole, right? And if you remove the south pole from a loop, it will be north pole.
Yeah.
Okay.
This is correct, but logic, you have to think this the solution of this question in some another way. Means, see
Alright.
the proper, actually this magnet is moving towards this now. So actually what you want, you want that this motion of the magnet should reduce or stop. So uh, here what pole should be there, because you are a student of physics, what pole should be there so that the motion of this magnet should stop. If there will be north pole, so north and north will repel. Suppose here is north pole and this is here is south pole, so they will repel means there will be some force of repulsion, so the motion of the magnet will be reduced now. Okay.
Yes, sir.
So in this way I think it will be better to think. Otherwise, if you will just say if north pole is moving towards north, then things will be messed up when you will. In the exam, sometimes you will get the questions like this. A magnet will be there and a coil will be there. The coil can be the in any shape. The coil can be the square shape, the rectangular shape, circular shape, it's mostly. And he or she will say, suppose the magnet is moving towards the coil, what is the direction of the induced current? Okay, what is the direction of the induced current? Then accordingly you will decide induced current. Write down this uh, on Matthew, on Monday there is Diwali on Monday.
I'm not sure, sir. I think there is, yeah.
So I think there will be no class on Monday. So okay, no problem. We'll see.
Sir, but we still have class, so.
Okay, if I think no, sorry. Okay, so if completed, then we will meet in the next class. And if there will be class on Monday, na, so please don't miss that class.
Okay, sir.
Because this Lenz law is very important part in from the for the exam point of view. Okay, if you have completed, then we will meet in the next class. And Nafisa, you stay.
Thank you, sir.
Okay, thank you. So Nafisa, are you free on Friday?
Yes, sir. Yes, sir.
Okay, so actually I am having the next class. So on Friday, na, on Friday we will discuss your question paper properly.
Yes, sir. Okay.
Okay, so basically Friday is my holiday, but I will take your extra class